Webb pointed at a patch of empty sky, a patch so small it would be covered by a grain of sand held at arm's length. When the image came back, astronomers went quiet. Thousands of galaxies filled the frame. Several were impossibly bright, impossibly massive, sitting in an era when none of them should have existed yet. We're about to walk through what Webb found, what it breaks, and why the people who built the models are now quietly rewriting them. We will track a galaxy chain 50 million light-years long that formed before it had any right to. We will meet black holes that grew too large too fast. We will follow a signal that keeps appearing across every deep field Webb has pointed at, in numbers that are statistically impossible to dismiss. If you find this kind of science worth your time, subscribing to Late Science takes 2 seconds and keeps this coming. The universe had a hidden early chapter. Webb just found the first pages. Prepare yourselves. We begin. The first Webb Deep Field image landed on scientists' screens in July of 2002, and within hours the messages started. Not press releases. Private messages between researchers. Informal, urgent, confused. The image showed a patch of sky so small that if you held a grain of sand at arm's length, it would cover it completely, and packed into that grain of sand-sized window were thousands of galaxies. That part was expected. Hubble had shown us deep fields before. What wasn't expected were the bright, compact red objects scattered through the image at distances that placed them in the universe's earliest chapters. There were too many of them. They were too bright. They were too massive. Every cosmologist who looked at that first image understood the same thing at once. The numbers were off. The James Webb Space Telescope didn't just give us sharper pictures. It gave us a fundamentally different kind of vision. Webb sees in infrared light, which means it captures wavelengths that older telescopes were essentially blind to. Light from the earliest galaxies has been traveling so long that the universe's expansion has stretched it far beyond visible range, deep into infrared. Hubble couldn't reach it. Webb was built for exactly this, and when it finally looked, what it found didn't match the map. Here's why that matters immediately. Every major cosmological model we have is built on decades of careful observation, mathematics, and simulation. The leading framework, called lambda CDM, makes specific predictions about how the universe evolved after the Big Bang. It says matter started nearly smooth, almost evenly distributed, and gradually clumped together under gravity over billions of years. Small structures first, larger ones later, a slow hierarchical build-up. That model has held up remarkably well across most of cosmic history. Webb started looking at the era that model was most confident about, the universe's first few 100 million to first couple billion years. The era when structure was supposed to be young, scattered, and modest, and instead it found large, organized, mature systems sitting exactly where the models said they shouldn't be yet. The word astronomers kept reaching for was tension. That's the scientific way of saying the prediction and the observation are pulling in opposite directions. A little tension can mean measurement error, a fluke, a gap in the data. The tension Webb started producing in that first year was something different. It was consistent. It appeared in multiple independent fields. It kept getting stronger the more data arrived. One early estimate from a team analyzing Webb's first deep imaging suggested the number of massive galaxies in the very early universe was potentially 10 to 100 times higher than lambda CDM predicted. That range is enormous, partly because confirming exact masses at those distances is difficult. But even the low end of that estimate is a significant problem, 10 times more than expected in a regime the model was confident about, is an alarm, not a footnote. This wasn't a single galaxy acting strangely. This was a pattern emerging across the deepest images ever taken of the early universe. And the pattern had a shape, a structure, something that implied matter had been organizing itself far earlier and far more efficiently than any simulation had ever managed to produce. The question forming in the background of every conversation wasn't whether the data was real. The question was what kind of universe produces results like this? And the answer to that question runs much deeper than one telescope's first image. What Webb was seeing wasn't just a collection of bright early objects. It was the edge of something much larger, hiding just behind the numbers. Before Webb, our picture of the early universe was built almost entirely on inference. We couldn't see it directly. The light was too faint, too stretched, too far into infrared for our best instruments to capture cleanly. So we built models. We used physics we trusted, mathematics that worked everywhere else, and computer simulations that could run the universe forward from the Big Bang and see what came out. The model that emerged from that process, lambda CDM, became the foundation of modern cosmology, and it made a clear, confident prediction about what the early universe looked like. Lambda CDM stands for lambda cold dark matter. Lambda refers to the cosmological constant, which describes dark energy, the force driving the universe's accelerating expansion. Cold dark matter describes the dominant invisible substance that provides most of the gravitational scaffolding for everything that forms. Together, these two ingredients, combined with ordinary matter, radiation, and the rules of general relativity, produce a model that correctly describes a remarkable range of observations: the large-scale structure of today's universe, the distribution of galaxy clusters, the faint glow of the cosmic microwave background, the oldest light we can detect, which maps the universe just 380,000 years after the Big Bang. The model says this: right after the Big Bang, matter was distributed with only tiny ripples of difference from place to place. Those ripples were the seeds of everything. Under gravity, slightly denser regions pulled in more material over time. The first structures to form were small, dark matter halos. Gas fell into those halos and cooled, allowing the first stars to ignite. Stars grouped into small proto-galaxies. Proto-galaxies merged over billions of years to build larger ones. Structure grew from the bottom up, slowly, steadily, across cosmic time. The timeline matters. According to lambda CDM, the universe at an age of 500 million years should look young, sparse clumps of star formation, irregular and modest, scattered through an otherwise thin and mostly unstructured cosmos. Massive, well-organized galaxies should come much later, after sufficient time has passed for mergers to stack mass together and gravity to pull everything into tighter configurations. That prediction was not a vague guess. It was a specific quantitative forecast. How many galaxies of a given mass should exist at a given redshift? How dense a region of the early universe should be? How much stellar mass could plausibly exist within the first billion years? These numbers were calculated, refined, and cross-checked against every observation available before Webb. The problem is that those predictions assumed we would never be able to directly test this particular error in detail. Hubble could probe the early universe, but incompletely. The infrared sensitivity required to clearly see galaxies at redshifts above 6, 7, 8, meaning galaxies from when the universe was under 1 billion years old, was simply beyond what existed before Webb launched in December of 2001. So the model was confident in a regime it had never truly been tested in. Webb changed that overnight. Every deep field image it returned from the early universe was a direct test of predictions that had been sitting untested for decades. And those tests are returning results the model wasn't built to expect. The architecture of the early universe, the one the model described in careful mathematical detail, is looking increasingly like a first draft. Something real is there in Webb's images, something the equations predicted much less of. And understanding why requires going back even further to the mechanism the model relies on most: dark matter. And whether it behaved in the early universe exactly as the model assumes. When you look at a star, you are looking into the past. That sounds like a poetic idea. It's a precise physical fact. Light travels at a fixed speed, roughly 186,000 miles per second. That speed is enormous on human scales, but the universe is far larger. The light reaching your eye from the nearest star beyond our solar system left that star over 4 years ago. You are seeing it as it was 4 years back. The star you are looking at may have changed. You won't know for 4 more years. Now scale that up to cosmological distances. Webb targets galaxies so far away that the light we capture from them has been traveling for over 13 billion years. The universe itself is only about 13.8 billion years old. That means some of the objects Webb images emitted their light when the universe was less than 1 billion years old. When we observe them, we aren't seeing what they are now. We are seeing what they were then, in the universe's first chapters. frozen in time by the speed of light. This is what cosmologists call look-back time. Every distance in the universe is also a duration. Farther away means earlier in time. Webb's ability to see extraordinarily distant objects means it can directly image the very young universe. Every image it returns from those distances is a real data point about the early cosmos, not an estimate, not a simulation output, an actual snapshot. The tool astronomers use to measure this look-back time is redshift. As the universe expands, the light traveling through it gets stretched. The wavelengths grow longer. Visible light shifts toward red. Infrared light shifts even further into longer infrared wavelengths. The amount of stretching tells you how much the universe has expanded since that light was emitted, which translates directly to how long ago it was emitted. A galaxy with a redshift of 2 existed when the universe was roughly 3 billion years old. A redshift of 6 puts you at under a billion years. A redshift of 10 or higher places you in the universe's first 500 million years. Webb has confirmed detections at redshifts above 10, and candidate observations pushing even higher. Here's what makes this powerful and what makes it alarming. Webb isn't just counting distant objects. It's measuring their properties: mass, stellar age, structure. When it finds a galaxy at a redshift of 7 or 8, it can estimate how much stellar mass that galaxy contains, and from the composition of the starlight, approximately how long those stars have been forming. Some of the massive galaxies Webb has found appear to contain stellar populations that are already hundreds of millions of years old, at a point when the universe itself is under a billion years old. That math creates an immediate problem. If a galaxy at a redshift of 7 already contains stars that have been forming for several hundred million years, it means star formation in that galaxy started extremely early, earlier than the model predicted star-forming conditions would exist at all in significant density. You're essentially looking at a finished building and calculating that construction must have begun before the land was available. The mechanism Webb relies on to reveal all of this, that deep infrared sensitivity, isn't just a technical upgrade, it's the key that opened a door the model assumed would stay shut a little longer. And behind that door, the pattern only gets more extreme the farther back Webb looks. In 2023, a study landed in the journals that used language cosmologists rarely allow themselves. The researchers, working with Webb's early deep field data, identified 6 galaxy candidates at extreme distances, all sitting in the universe's first 700 million years. When they estimated the stellar masses of those galaxies, the numbers came back far above anything Lambda CDM predicted should exist that early. One candidate appeared to contain a stellar mass comparable to the Milky Way, sitting at a redshift that placed it in the universe's first 500 million years. The researchers called them un-universe breakers. That phrase wasn't hyperbole for a press release. It was a direct statement about the relationship between the observation and the model. If confirmed at full mass, these galaxies would require more stellar mass to have assembled in the first 500 million years than the standard model's physics can produce. The caveat matters. Some of those 6 candidates have since been refined. Spectroscopic follow-up, the deeper analysis that confirms distances and mass estimates precisely, has adjusted some numbers. A few turned out slightly less extreme than the initial photometric estimates suggested, but several held up. And the broader pattern they represented, large masses appearing too early, has not gone away with better data. If anything, more Webb observations across different fields have reinforced it. Here's the core of why this is so difficult to explain away. In Lambda CDM, the amount of stellar mass a galaxy can build is limited by a chain of processes. Dark matter halos form first, and their growth rate is constrained by the physics of structure formation. Gas falls into those halos on a specific timescale. Stars form from that gas at a rate limited by how efficiently cold gas can collapse under gravity and shed heat. Each step in that chain takes time, real, calculable amounts of time determined by well-tested physics. To build a galaxy with Milky Way-scale stellar mass in 500 million years, you would need to run every step in that chain at efficiencies far beyond what any known process supports. The gas would need to cool faster. Stars would need to form from it faster, and all of it would need to start forming before the models say the conditions for it even existed. Think of it as trying to grow a full-sized oak tree in a pot the size of a coffee cup over a weekend, using soil that was only just created. The tree exists. We can see it. The cup, the soil, and the weekend don't add up to produce it under any rule we currently know. Some researchers have proposed partial explanations. Early, extremely efficient star formation bursts, a possible contribution from active galactic nuclei, meaning black holes at the galaxy's centers, adding luminosity that inflates mass estimates. Dust effects that alter how we interpret the light. These are real possibilities that remain under active investigation. They may reduce some of the tension. The trouble is that none of them resolves it completely, and Webb keeps adding more galaxies to the list. Each new data release doesn't calm the problem, it deepens it. And it pushes the question further back in time, toward an era when the explanations get thinner and the structures get stranger. In 2004, a team announced a structure unlike anything previously confirmed at such an early epoch. They called it the Cosmic Vine. At first, the name sounds like something from a nature documentary. It describes something genuinely alien. The Cosmic Vine is a long, filamentary chain of at least 20 massive galaxies, all physically linked, all gravitationally associated, stretching across a distance of roughly 50 million light-years. And it exists at a redshift of approximately 3.3, meaning we observe it as it was when the universe was around 2 billion years old. 2 billion years sounds like a long time, but the universe is 13.8 billion years old. At 2 billion years in, the universe was only about 15% of its current age. The cosmic vine was already organized, massive and coherent, at a point when, according to standard models, large-scale structure of that kind was still in early assembly. The structure was identified using data from Webb, alongside earlier Hubble imaging, and the team confirmed the physical association of its member galaxies through detailed analysis of their positions and light profiles. This wasn't a projection effect, where unrelated galaxies happen to line up along the line of sight. The galaxies are genuinely clustered together in three-dimensional space. They form a real filament, a thread of organized cosmic structure, at an epoch when such threads were expected to be far less defined. Filaments are a fundamental feature of the universe's large-scale structure. On the grandest scales, the cosmos looks like a cosmic web, vast sheets and threads of matter surrounding enormous empty voids. Galaxy clusters tend to sit at the intersections of these filaments. Galaxies flow along them. The web itself is real, confirmed by decades of observation. But standard models predict this web to be relatively underdeveloped in the early universe, with filaments becoming clearly defined only as billions of years of gravitational accumulation build them up. The cosmic vine is a defined filament, at a time when defined filaments shouldn't be this coherent or this massive. It implies that the gravitational skeleton of the universe began organizing itself earlier and more aggressively than the models calculate. What makes it especially significant is the size and number of its member galaxies. These aren't small proto-galaxies. Several are already massive systems. For that many massive galaxies to be co-located in a filamentary structure at that epoch, they had to have been assembling their mass even earlier, beginning their formation in the universe's first few 100 million years to arrive at this state by the 2 billion year mark. The cosmic vine is effectively a record of a party that started well before astronomers thought the venue existed. And here's what makes it a forward-pulling signal, rather than just an isolated discovery. Filaments are pathways. Matter flows along them toward clusters. If a filament this organized existed at 2 billion years, then the cluster it's feeding, the dense knot of galaxies forming at its center, was also assembling early, possibly far earlier than the models account for. The vine isn't a curiosity. It's evidence that the large-scale architecture of the universe had a head start. And the source of that head start points towards something the model built its entire foundation on. The universe has a shape. On the largest scales, matter doesn't distribute randomly. It arranges itself into a vast three-dimensional web. Enormous sheets and filaments of galaxies and dark matter surround colossal empty regions called voids. Where filaments cross, matter piles up into massive galaxy clusters. This pattern, the cosmic web, looks roughly like a sponge seen from the inside, with structure everywhere and vast emptiness in between. We've known the cosmic web exists at late cosmic times, Massive surveys like the Sloan Digital Sky Survey mapped it across billions of light years in the relatively recent universe. The Webb is real, measurable, and broadly consistent with what lambda CDM predicts for those epochs. The critical assumption baked into the model is that the Webb was far less developed in the early universe. At the billion-year mark, filaments should be wispy, vague, and barely coherent. Large clusters should be rare. The Webb's skeleton should still be forming, like scaffolding just beginning to rise from a foundation. Webb is challenging that assumption directly. The cosmic vine is one data point, but the broader Webb dataset is showing that in field after field, at redshifts of 3, 4, 5, and beyond, the large-scale structure appears more organized, more filamentary, more developed than simulations running the standard physics predict. Overdense regions, places where galaxies are clustering together unusually tightly, keep appearing in Webb's images at epochs where the model says the universe should still be mostly smooth. An overdense region is exactly what it sounds like, a patch of the universe where matter has piled up above the average. In the early universe, overdense regions are the seeds of future clusters. The denser a region, the earlier it began collecting material. Finding a highly overdense region in the early universe tells you that matter was concentrating itself far ahead of schedule. One confirmed example is a protocluster detected at a redshift of approximately 7.9, placing it in the universe's first 700 million years. At that distance and that epoch, a coherent overdensity of galaxies was confirmed using Webb spectroscopic instruments. Multiple galaxies in a localized region, physically associated, forming a gravitational system together. Protoclusters at such extreme redshifts are exactly what the model predicts should be extraordinarily rare. Finding one isn't proof the model is broken. Finding a growing catalogue of them across independent survey fields, with Webb's different survey programs all returning similar results, creates a statistical weight that individual anomalies don't produce. Here's the underlying problem in plain terms. For the Webb skeleton to be this developed this early, the seeds had to have been larger than the model allows. The tiny ripples of density that existed just after the Big Bang, the ones that became everything, had to have been slightly more extreme, slightly more uneven, than our best measurements of the cosmic microwave background currently suggest. This is where the observational tension starts touching theory at a very deep level, because those early density ripples, called primordial fluctuations, aren't something we can adjust freely. They're constrained by what we see in the oldest light in the universe. If Webb's early structure keeps outpacing predictions, the answer may require going all the way back to the very first fractions of a second after the Big Bang, to a process that set the initial conditions for everything that followed. And the current best candidate for that process has its own unresolved problems. Growth in the universe follows a specific sequence. Dark matter moves first. It doesn't interact with light, so in the early universe, when radiation pressure was keeping ordinary matter spread out and smooth, dark matter was free to start clumping under gravity. It pulled together into invisible halos, regions where the density of dark matter was above the cosmic average. Those halos were the first gravitational traps the universe built. Then, ordinary matter fell in. As the universe cooled and expanded, hydrogen and helium gas began streaming into those dark matter halos. Inside the halo, the gas was no longer free-flowing. Gravity pulled it inward, and as it compressed, it heated up. For stars to form, the gas needed to cool down again, shedding energy as radiation, becoming dense and cold enough for gravity to collapse pockets of it into stars. This cooling process takes time, dictated by atomic physics that doesn't bend to circumstance. When gas finally cooled enough, star formation could begin. Stars formed in groups, building the first stellar populations inside small proto-galaxies. Those proto-galaxies were themselves caught in larger dark matter halos. Over billions of years, smaller halos merged into larger ones, pulling their galaxy cargo with them. Proto-galaxies merged to form larger galaxies. Galaxies merged to form giants. The whole process cascades upward, building the large-scale structure from the bottom up. Lambda CDM calls this hierarchical structure formation, and it works extremely well for describing the universe we see at late times. the distribution of galaxy clusters today, the mass functions of galaxies in the nearby universe, the properties of the cosmic web on large scales, all of it largely matches what hierarchical formation predicts. The flaw in applying this story to what Webb is finding is timing. Each step in that sequence has a minimum duration. The dark matter halos need time to collect mass. Gas cooling has a rate that depends on density and temperature and atomic cross-sections. Star formation has an efficiency ceiling imposed by feedback. When stars form, they emit radiation and eventually explode as supernovae, which heat the surrounding gas and slow further star formation. These breaks on the process are well established from observations of galaxies in the nearby universe. Stack all those timescales together, and the model produces a clear prediction. A galaxy with stellar mass comparable to the Milky Way should require several billion years to assemble. Structures with multiple such galaxies organized into clusters should require even longer. What Webb is showing is that something is compressing that timeline. The structures it finds appear to have assembled a significant fraction of their mass within the first 1 to 2 billion years. At star formation efficiencies that would require either an entirely different physical process or a breakdown of the feedback mechanisms that slow star formation in the modern universe, or conditions in the early universe that gave gravity and gas cooling a much earlier and more powerful head start than the model provides. The debate is now centered on which of those explanations holds. Each one has a different implication, and one of them, if correct, means revising something the model has treated as settled since the 1990s. They weren't supposed to exist, and yet there they were, 6 of them, scattered across Webb's early deep field data, each one carrying a mass that made the equations uncomfortable. The study was published in February of 23 by a team led by Ivo Labi and colleagues. The 6 candidate galaxies all appeared at extreme redshifts, placing them within the universe's first 700 million years. Their estimated stellar masses was startling. The most extreme candidate appeared to carry a mass of roughly 100 billion times the mass of our star, at a cosmic age when nothing that massive was supposed to have had time to form. The team themselves used careful, measured language in the paper. They described the candidates as challenging standard galaxy formation models, and noted that if the mass estimates held under spectroscopic confirmation, the standard model would require revision. The phrase universe breakers came from a co-author speaking to the press, but it reflected a real mathematical point. You cannot build that much stellar mass that fast, under the rules the model relies on. Here's the specific problem. Building a galaxy with 100 billion solar masses of stars in under 700 million years requires a star formation rate, sustained over that entire period, that sits well above what any observed galaxy today achieves even in its most active phase. Modern starburst galaxies, galaxies forming stars at extraordinary rates, do so in intense but brief episodes, sustaining that level of output for hundreds of millions of years, without feedback from radiation and supernovae shutting the process down, conflicts with what we observe in the current universe. One possible partial explanation is that early galaxies had a higher star formation efficiency before the feedback mechanisms that dominate today became as effective. Some theoretical work suggests early galaxies may have been denser, more compact, with gas conditions that allowed faster collapse into stars. This is a real hypothesis under investigation. Another possibility involves how we measure mass. Photometric mass estimates, the ones drawn from imaging data alone before spectroscopy, can carry significant uncertainties. Active galactic nuclei, black holes at galactic centers that are actively feeding and radiating intensely, can add luminosity that gets misinterpreted as stellar mass. If a fraction of the apparent brightness in these galaxies comes from an active nucleus rather than purely from stars, mass estimates could be inflated. Follow-up spectroscopic analysis has refined several of the original 6 candidates. Some came down in mass, some remained alarming. The overall conclusion of the field has not been that the original study was simply wrong. It has been that the signal is real, the anomaly is genuine, and the full extent of it is still being quantified. New Webb surveys continue returning massive early galaxies. The 6 from the Labe study weren't a fluke. They were the first clear signature of something the model had never been forced to confront directly. And sitting at the center of several of these too massive too early galaxies is a second problem that compounds the first. a problem that was already uncomfortable before Webb launched, and that Webb has now made significantly harder to dismiss. Understanding how far Webb is really looking requires grasping one of the most elegant and unsettling facts in all of physics. The universe is expanding. Every large-scale region of space is moving away from every other region. This isn't galaxies flying through space like shrapnel from an explosion. Space itself is stretching. The fabric of the cosmos is getting larger in every direction simultaneously. Now consider what that does to light. Light traveling through expanding space doesn't travel through a static medium. The space it moves through stretches while the light is in transit. That stretching acts on the light's wavelength, making it longer. Longer wavelengths correspond to redder colors in visible light. The further the light has traveled, and the more the universe is expanded during that journey, the more the wavelength stretches. This stretching is what astronomers measure as redshift. They look at the spectrum of a distant galaxy, identify the fingerprint patterns of specific elements like hydrogen, and compare where those patterns appear in the spectrum to where they appear in a laboratory on Earth. The amount the pattern has shifted toward longer wavelengths is the redshift value. A redshift of 0 means the object is essentially sitting still relative to us. A redshift of 1 means the universe has expanded by a factor of 2 since the light was emitted, placing the emission event around 6 billion years ago. A redshift of 6 means the universe was about 1/7 its current size when that light left, corresponding to an age of under a billion years. A redshift of 13 corresponds to the universe being roughly 3% of its current age, just over 100 million years after the Big Bang. Webb has confirmed galaxy detections at redshifts above 13. One galaxy, designated by researchers as among the most distant, spectroscopically confirmed objects, sits at a redshift of approximately 13.2, placing its light emission at around 320 million years after the Big Bang. This measurement is direct. Spectroscopy doesn't depend on assumptions about galaxy brightness or size. It reads the actual wavelength shift in the emitted light. When a galaxy confirms at redshift 13, it means we are genuinely observing a galaxy as it existed 320 million years after the universe began. What makes that number alarming in context is what those galaxies look like. They already contain populations of stars. Some already show signs of organized structure. They aren't wispy clouds of slowly assembling hydrogen. They're already doing things. At 320 million years old, the universe itself is barely a fraction of the age required to produce them under standard formation models. Here's what that means for everything Webb is measuring. Every galaxy it finds at extreme redshift isn't a curiosity about one unusual object. Each one is a data point about the conditions that existed in the universe at that time. Each one tells you something was already organizing, already forming, already building stellar mass, far earlier than the model scheduled those processes to begin. And when data points start clustering in ways the model doesn't predict, the pressure falls on the model to explain what it got wrong. Cosmological simulations are among the most sophisticated tools science has ever built. Programs like Illustris TNG and Eagle take the known laws of physics, set the initial conditions of the universe shortly after the Big Bang, and then run the universe forward in time. Gravity pulls matter together. Gas flows and cools. Stars form and die. Black holes grow. Feedback from supernovae and active galactic nuclei spreads energy back into the surrounding gas. Over billions of simulated years, galaxies assemble, merge, and evolve. These simulations have been validated against observations of the nearby universe extensively. They reproduce the distribution of galaxy masses we see today. They produce cosmic web structures that match large-scale surveys. They generate galaxies with properties that match observed populations across much of cosmic history. They are among the best-tested theoretical tools in any scientific field. Webb is testing them in a regime they were never challenged in before, the very early universe. And across multiple independent simulation codes running on the most powerful supercomputers available, the results are consistent. At the redshifts where Webb is finding massive, organized galaxies and coherent filamentary structures, the simulations produce far less. In some comparisons, the simulated number of massive galaxies at high redshift falls short of what Webb observes by factors of 10 to 100. The exact factor depends on the mass threshold and the specific dataset being compared, but the direction of the discrepancy is stable across studies. That consistency is meaningful. When different simulation frameworks, built by different teams using somewhat different methods, all fail in the same direction against the same observations, the failure is telling you something real. The physics baked into the simulations is missing something, or something it assumed about the early universe is incorrect. The most common proposed fixes fall into a few categories. One possibility is that star formation in the early universe was more efficient than it is today, meaning simulations are using star formation prescriptions calibrated on modern galaxies that don't apply at high redshift. Another is that early feedback processes, the mechanisms that slow star formation in simulations, were weaker in the early universe, allowing galaxies to grow more rapidly. A third possibility, more radical, is that the initial conditions themselves were different, that the early universe had larger density fluctuations than the simulations assume, giving gravity a bigger head start. Each of these fixes has constraints. Changing star formation efficiency at high redshift has to remain consistent with what we observe when we look at galaxies in the intermediate universe, the period between Webb's extreme targets and today. The simulations also have to keep matching all the observations they already match. Threading that needle is the challenge now facing cosmological modelers. They are working to update simulations to incorporate Webb's findings without unraveling everything that already works. Some researchers argue the simulations only need targeted adjustments. Others argue the adjustments required are large enough that they point toward a more fundamental gap in the model. The gap is now measurable. What fills it is still genuinely unknown. Dark matter holds the universe together. That sentence is literal. Without dark matter, galaxies wouldn't hold their shape. Stars at the outer edges of galactic disks rotate too fast to be held by the gravity of visible matter alone. Something invisible, something that doesn't emit or absorb light but does exert gravitational pull, must be there in enormous quantity. That something is dark matter. It constitutes roughly 27% of the total energy content of the universe. Ordinary matter, everything we can see and touch, accounts for only about 5%. Dark matter's gravitational influence dominates structure formation. The cosmic web, the filaments, the halos that galaxies form inside, all of it is dark matter scaffolding that visible matter fills in later. Lambda CDM's specific assumption is cold dark matter. Cold means the dark matter particles were moving slowly relative to the speed of light in the early universe. Cold particles clump more easily, forming small halos first, which then merge into larger ones over time. This bottom-up hierarchy is central to how the model works. The early structure Webb is finding creates an interesting pressure on this assumption. Specifically, if the dark matter halos that seed early galaxies were somehow larger, or formed faster, or were more concentrated than cold dark matter predicts, you could naturally produce the massive, organized structures Webb is seeing. The dark matter blueprint would be more aggressive, and the galaxies forming inside it would match that blueprint. One alternative framework that has received renewed attention in light of Webb's findings involves warm dark matter. Warm dark matter particles would have been moving faster than cold ones in the early universe, which suppresses the formation of very small halos, but could, under certain models, produce different large-scale behavior. The relationship between warm dark matter and early structure formation is complex, and the current consensus still favors cold dark matter as the better fit overall. Another proposal involves what physicists call primordial black holes as a dark matter candidate. If a significant fraction of dark matter consisted of black holes formed in the very early universe, before galaxies existed, they could have seeded structure formation differently and potentially earlier than particle dark matter alone. This remains speculative and contested. What's confirmed is that cold dark matter models, as currently calibrated, don't naturally produce the halos needed to generate the masses and structures Webb is observing at the epochs it's observing them. Whether the fix requires adjusting dark matter's properties, adjusting the initial conditions it was given, or adjusting something else entirely remains an open question. And here's the thread that connects dark matter to something deeper. Dark matter's behavior in the early universe was partly shaped by the conditions at the Big Bang itself, specifically by what happened in the first fractions of a second during a violent period of rapid expansion, called inflation. If the density fluctuations that inflation produced were slightly different from what models assume, dark matter halos would have formed differently. Earlier, larger. Inflation is where several independent lines of tension in modern cosmology now seem to converge. 73 years after the Big Bang ended, something happened that almost no one predicted at the time. The universe's expansion, which had been gradually slowing as gravity worked against it, began to speed up again. This acceleration has been confirmed by multiple independent lines of evidence. Observations of distant supernovae in the late 1990s revealed that the universe's expansion rate today is higher than expected if gravity alone were in control. The data required a new ingredient, something with negative pressure, acting against gravity on cosmological scales. Scientists called it dark energy, and in lambda CDM it is represented by the Greek letter lambda, a constant value spread uniformly across all of space that pushes the universe's expansion to accelerate. Dark energy accounts for roughly 68% of the total energy content of the universe. It dominates the universe's total energy budget, and in the current era, it is the primary driver of how the universe grows. Lambda CDM treats dark energy as a cosmological constant, a fixed, unchanging value. That's the simplest possibility. But whether it truly is constant across all of cosmic time, or whether it varies, is one of the key open questions in cosmology. In the early universe, dark energy's effect was relatively small compared to the gravitational pull of all the matter present. The universe was dense, matter dominated, and structure formation was proceeding under gravity's rules. Dark energy was there but subdued. The model treats it as essentially negligible in the very early epochs where Webb is now finding its anomalies. This is where a subtle but significant debate has emerged. Some theoretical proposals suggest that dark energy may have had a different value or behavior in the early universe than it does today. If dark energy had even a slight early enhancement, it could in principle affect the rate at which density perturbations grew, potentially giving structure formation a mild extra push. This remains highly speculative. Current data from the cosmic microwave background don't strongly support a major variation in dark energy at early times. But in 2024, the Dark Energy Spectroscopic Instrument, a large ground-based survey, released preliminary results suggesting that dark energy may show a slight variation over cosmic time, meaning it may have changed in strength as the universe aged. This finding was described by the collaboration as early and requiring further confirmation. It was enough to reopen a question that many researchers had considered largely settled. If dark energy did vary even slightly, the implications for early structure formation are non-trivial. Models would need to be updated to track how its changing value affected the growth of density perturbations across cosmic time. For now, dark energy's potential role in Webb's anomalies is one of several open threads. It may contribute. It may not. The honest answer from the field is that no single proposed mechanism fully resolves the mismatch, and the data continues to arrive faster than the theoretical revisions can comfortably keep pace. There is another source of pressure, one that Webb has now brought into sharp focus. And it doesn't come from dark energy or dark matter. It comes from something far smaller, far earlier, and far harder to directly observe. In the universe's first 700 million years, finding a single massive galaxy is alarming enough. Finding a coherent group of them, gravitationally bound together, forming a system, is a different category of finding entirely. A galaxy cluster is one of the largest gravitationally organized structures in the universe. Today's clusters contain hundreds to thousands of galaxies, enormous quantities of hot gas, and dark matter halos with masses reaching thousands of times the mass of the Milky Way. They form at the densest intersections of the cosmic web, where matter has been piling up and merging for billions of years. In the early universe, the precursors to clusters are called protoclusters. A protocluster is a region where multiple galaxies are already collecting in a localized overdensity, on their way to eventually merging into a true cluster over billions of years. Protoclusters at moderate redshifts corresponding to the universe at a few billion years old have been known for some time. They're rare but not shocking at those epochs. Webb has confirmed protocluster structures at redshifts approaching and exceeding 8. One particularly notable example sits at a redshift of around 7.9, placing it in the universe at roughly 700 million years of age. At that location, Webb detected a grouping of galaxies within a compact region that showed signs of physical association, meaning they are genuinely co-located in three-dimensional space rather than projected chance alignments. What makes this discovery structurally significant is the implication for mass and timing. For multiple massive galaxies to be gravitationally associated at that epoch, the dark matter halo hosting them had to have assembled an extraordinary amount of mass in under 700 million years. That mass wasn't carried in gently. It was gathered by gravitational collapse from the surrounding region, which means the surrounding region had to have an above-average density of matter from very early on. Trace that back to its origin, and you arrive at the same place every Webb anomaly eventually points: the initial density field left by the Big Bang and the period of rapid expansion that shaped it. If the seeds were bigger in certain regions, overdensities grew faster, halos formed earlier, and protocluster environments were in place far ahead of the timeline the model currently uses. This isn't a small numerical adjustment. Protocluster environments at redshift 8 require the seeding of those overdensities at a level that current measurements of the cosmic microwave background don't obviously predict. The cosmic microwave background's temperature fluctuation map is our best measurement of those primordial seeds. If the seeds required to produce Webb's early clusters are larger than the cosmic microwave background suggests they should be, there is a genuine inconsistency between two of our most trusted observational windows. That inconsistency is not yet confirmed at a level that forces a model revision, but it's not zero. Researchers are now working to determine whether the tension is a measurement issue, a sampling fluke, or a real signal from the early universe. One of the sharpest tools for probing this is Webb's spectroscopic capability, which doesn't just tell you where a galaxy is, but what it's made of, how fast it's forming stars, and what its internal dynamics look like. And what spectroscopy is finding inside these early galaxies is adding yet another layer to the problem. A single unusual galaxy can be explained away. It could be a measurement error, a rare statistical outlier, a quirk of how light travels through the intervening universe and distorts our view. One anomalous data point, however striking, doesn't overturn a well-tested framework. Science accounts for outliers. What you cannot as easily dismiss is a collection of massive galaxies, all in the same physical region of space, all at the same cosmic epoch, all showing properties that conflict with predictions. A cluster, or a protocluster, carries combinatorial weight that single detections simply don't. Here's the statistical logic. If the probability of finding one very massive galaxy at a given high redshift, under current models, is already low, perhaps one in several thousand, then finding multiple massive galaxies in the same small volume of space, at the same redshift, isn't one improbable event. It's several improbable events co-occurring, which under standard statistical reasoning requires either a systematic bias in the measurement, a flaw in the model, or a genuine physical mechanism that the model doesn't include. Systematic biases are always the first thing researchers check. Could gravitational lensing, the bending of light by intervening mass, be amplifying the apparent brightness of background galaxies and making them appear more massive or more numerous than they are? Lensing is a real effect, well understood, and in some specific fields it does boost apparent numbers. Webb survey teams correct for it where it can be measured. Could selection effects be at play, where the way surveys are designed make certain types of galaxies preferentially detectable, creating a false impression of abundance? This is also carefully examined. The surveys showing high numbers of early massive galaxies use multiple independent methods to test for selection biases. After those checks, the excess remains. Several independent survey programs using Webb have found consistent elevated numbers of massive galaxies at high redshift. The programs differ in area, depth, target selection, and analysis methods. Their agreement isn't a coincidence of methodology. It reflects something real in the data. What a protocluster finding adds beyond individual galaxies is physical coherence. The galaxies aren't just individually anomalous. They're organized. They're gravitationally interacting. They're sharing an environment and apparently sharing a formation history. That organization is itself information. It means the overdense region that spawned them was real and significant, not a random accumulation of unrelated outliers. Organized early structures also tell you something about what comes next in cosmic history. A protocluster at redshift 8 will, over the following billions of years, continue collecting matter, merging its component galaxies, heating gas, and eventually becoming one of the massive galaxy clusters we observe at lower redshifts. If Webb's early protoclusters are real and numerous, they imply a specific distribution of massive clusters in the intermediate universe, a prediction that future surveys will be able to test. That predictive chain is how the tension becomes most scientifically productive. Webb's early universe findings aren't just anomalies to shrug at. They're constraints that ripple forward through cosmic time and can be tested against independent observations. And one of the mechanisms that could explain the formation of these early organized structures brings us back to a process happening inside the galaxies themselves, at a rate that has no modern analog. The Milky Way forms stars at a leisurely pace by cosmic standards, roughly 1 or 2 new stars per year, on average, spread across a disk 100,000 light-years wide. That rate reflects the current state of the galaxy, mostly settled, with its gas supply partially exhausted, feedback processes regulating the conversion of gas to stars at a slow, steady equilibrium. We live in a galaxy in a relatively quiet phase of its star-forming life. Some galaxies today are far more active. Starburst galaxies, triggered typically by collisions or mergers with other galaxies, can form stars at rates 100 to 1,000 times higher than the Milky Way. These bursts are intense but short-lived. The feedback from the newly formed stars, radiation pressure, stellar winds, and eventually supernova blasts, heats the surrounding gas and shuts the burst down within tens to hundreds of millions of years. Webb is finding evidence that some early massive galaxies were forming stars at rates that dwarf even the most extreme modern starbursts, and sustaining those rates for far longer than any feedback mechanism in current models should allow. For a galaxy to accumulate the stellar mass Webb is measuring in these extreme early systems, within the time available, the star formation rate would have had to be extraordinary. Calculations suggest some of these galaxies were converting available gas to stars, at efficiencies approaching 100% across extended periods. In modern galaxies, star formation efficiency rarely exceeds a few percent of the available gas, before feedback shuts the process down. There are several competing explanations for how this could happen. One centers on the physical conditions of the early universe itself. The gas in the early universe was primarily hydrogen and helium, with almost none of the heavier elements produced by stellar fusion that modern gas clouds contain. This metal-poor gas behaved differently under gravity. It may have been more prone to rapid, efficient cooling and collapse, allowing it to fall into star-forming pockets faster than enriched gas does today. Some theoretical work suggests that metal-poor gas environments could produce star formation efficiencies significantly higher than anything we observe now. A second possibility involves the structure of early galaxies. Several of the very early massive galaxies Webb has resolved appear to be compact and dense, with star-forming regions packed into much smaller physical volumes than in modern galaxies. High density accelerates the collapse of gas clouds, potentially allowing a faster conversion of gas to stars before feedback has time to build up and interrupt the process. A third, more contested possibility is that some massive early galaxies experienced sustained accretion of fresh gas from the cosmic web along cold filamentary streams, constantly replenishing their star-forming fuel before feedback could exhaust it. This cold accretion model is theoretically supported, but difficult to confirm observationally at extreme redshifts. None of these explanations is yet proven to fully account for the mass assembly rates Webb implies. Each one works partially in certain parameter regimes for certain galaxy types. Together, they may get closer to an explanation. But alone, none of them cleanly resolves why the early universe consistently appears to have built so much, so fast, across so many independent lines of observation. And inside many of these early, vigorously star-forming galaxies, something else is also growing at a rate that should be equally impossible. Before Webb, this entire chapter of the universe's story was essentially invisible to us. To understand why, you need to picture what happens to light over 13 billion years of travel through an expanding universe. The expansion stretches wavelengths. Light that began its journey in the ultraviolet or visible range, arrives at Earth having been redshifted far beyond what the human eye or a conventional optical telescope can detect. The most distant galaxies Webb targets emit their light in wavelengths that arrive shifted deep into the infrared, between 1 and 5 microns in wavelength. Hubble Space Telescope, which transformed our understanding of the cosmos across 3 decades of operation, had limited infrared capability. Its main instruments were optimized for visible and near ultraviolet light. When it attempted observations at the edges of its infrared range, it could reach galaxies at redshifts up to around 10 or 11 in exceptional cases, but with limited sensitivity and very long exposure times. The very early universe was, for Hubble, at the edge of detectability, not a regime it could survey systematically. Ground-based telescopes face the additional problem of Earth's atmosphere, which absorbs infrared wavelengths in several key bands. Even the best ground-based infrared observatories are partially blocked by the air itself, restricting what they can detect at these wavelengths. Webb was designed from the ground up to solve both problems. It operates above the atmosphere entirely, giving it access to the full infrared spectrum. Its mirror, 6.5 meters across and composed of 18 gold-coated beryllium segments, collects roughly 6 times more light than Hubble's mirror. Its instruments, particularly the near-infrared camera and the near-infrared spectrograph, are engineered for extreme sensitivity in exactly the wavelength range where early galaxy light arrives. The telescope operates at a temperature of around -380 degrees Fahrenheit, extremely close to absolute zero, because its own infrared emission would otherwise drown out the faint signals it's trying to detect. It sits at a gravitationally stable point, about 1 million miles from Earth, facing permanently away from the warmth of Earth and the star it orbits, shielded by a tennis court-sized sun shield that keeps its instruments in permanent deep cold. Every one of these engineering choices was made specifically to reach the early universe. When Webb captures an image and you see a field packed with thousands of galaxies of various shapes, sizes, and colors, you are looking at the result of that engineering. The faint red smudges at the edge of detection in those images are often galaxies from the universe's first billion years, whose light no prior instrument could capture in this detail. But detecting a galaxy in an image is only the first step. To confirm its distance and to measure its properties precisely enough to create the kind of scientific tensions we've been discussing, astronomers need spectroscopy. Spectroscopy is where Webb's infrared spectrograph earns its place in this story. And what it's been returning from the early universe goes well beyond just confirming distances. Every time a new Webb discovery makes headlines, 2 words carry most of the scientific weight: confirmed and candidate. They are worlds apart. A candidate galaxy at extreme redshift means a galaxy whose distance has been estimated from its colors and brightness across multiple imaging filters. This technique, called photometric redshift estimation, works by comparing the brightness of the galaxy across different wavelength bands and fitting that pattern to models of how galaxy light looks at different distances. It's powerful, fast, and allows researchers to identify thousands of potential high redshift galaxies from imaging data alone. But photometric estimates carry uncertainty. A galaxy that looks like it should be at a redshift of 12 could, under some circumstances, be a foreground galaxy at a much lower redshift that happens to have unusual dust properties or unusual spectral features. Contamination by these low redshift interlopers has historically inflated high redshift galaxy counts in some surveys. The fraction of photometric candidates that turn out to be genuine extreme redshift objects varies, but it can be substantial in some selection methods. Spectroscopic confirmation is a completely different process. The near-infrared spectrograph on Webb disperses the light from a galaxy into its component wavelengths, producing a detailed spectrum. In that spectrum, astronomers look for specific atomic emission or absorption lines. The fingerprints of hydrogen, oxygen, carbon, and other elements appearing at shifted wavelengths that directly encode the galaxy's redshift. A spectroscopic redshift is precise. It doesn't depend on model fitting across broad wavelength bands. It reads the actual shifted atomic lines. When a galaxy confirms spectroscopically at a redshift of 13, that number carries a very small uncertainty. The galaxy genuinely is that distant. Its light genuinely left it 300 plus million years after the Big Bang. This distinction matters enormously for interpreting the Webb findings on early structure. Many of the most dramatic initial announcements from Webb, including the universe breaker galaxies and several extreme proto-cluster candidates, began as photometric detections. The scientific alarm they generated was real but appropriately provisional. As spectroscopic follow-up has arrived, a consistent pattern has emerged. Some candidates come down in redshift upon confirmation, turning out to be at lower distances than the photometry suggested. A meaningful fraction, enough to be statistically significant, confirm at or near their photometric estimate. And some of the confirmed spectroscopic detections are alarming enough on their own, without needing the full photometric sample, to create genuine tension with the models. One example is a spectroscopically confirmed galaxy from the JADES survey, a deep Webb program targeting a well-studied patch of sky. Several galaxies in that survey confirmed at redshifts above 11, with one of the most distant spectroscopic confirmations in the early program sitting at a redshift of around 13.2. These aren't estimates. These are measured distances. What spectroscopy also delivers is composition. The ratios of different atomic emission lines in a galaxy's spectrum tell researchers about the temperature and density of its gas, the abundance of heavy elements, and the dominant source of energy, whether mostly starlight, an active nucleus, or a mix. And several spectroscopically confirmed early galaxies are showing chemical and structural features that imply their stellar populations are older than their observed epoch alone would suggest. Stars that appear old inside a very young galaxy mean those stars began forming even earlier, which means the formation process reaches back further than the observed snapshot. And in some of these early systems, Webb spectrograph is catching something else entirely, something with a very different energy source. Webb found them in almost every deep field it pointed at. Small, compact, intensely red objects scattered through the early universe in numbers that didn't match any prediction. Researchers called them little red dots, a name that sounds almost dismissive, but describes something genuinely strange. These objects appear across multiple independent Webb survey programs, at redshifts placing them in the universe's first 1 to 2 billion years, and they are doing something that current models struggle to explain. The strangeness comes from what their spectra reveal. When Webb spectrograph breaks their light into component wavelengths, many of these objects show signatures of two simultaneous processes happening at extraordinary intensity, strong emission lines that indicate rapid star formation, with young hot stars flooding their surroundings with ultraviolet radiation, and equally strong signatures consistent with a rapidly feeding supermassive black hole at the galaxy's center, called an active galactic nucleus, pouring out its own intense radiation as it consumes surrounding gas. In the nearby universe, galaxies do both these things, but rarely simultaneously at such extreme levels, and almost never in such compact physical volumes. Star formation and black hole feeding tend to regulate each other. The energy released by an active nucleus heats and expels gas from the galaxy's center, reducing the fuel available for star formation. This feedback loop is one of the key mechanisms cosmological simulations use to reproduce realistic galaxy populations. The little red dots appear to be violating this balance. They are forming stars and feeding their central black holes at the same time, at rates that models say should be self-limiting, inside objects far smaller and denser than typical galaxies at any epoch. Their compactness is itself a puzzle. Many of these objects are physically tiny compared to modern galaxies, some compressed into regions less than 1,000 light-years across, while containing stellar masses and black hole masses that would be impressive in a much larger system. Whether this compactness is a fundamental feature of early galaxy formation, or a phase that later puffs out into normal-looking galaxies, is still under active investigation. A study published in 2024, examining a large sample of little red dots, found that their number density, meaning how many of them exist per unit volume of the universe, exceeds what any pre-Webb model predicted by a significant margin. They aren't just individually unusual. There are too many of them for the models to easily accommodate. One proposed explanation is that the little red dots represent a very brief, but very intense phase of simultaneous black hole and star formation activity, a kind of dual burst that the model's feedback timing simply doesn't predict occurring this frequently. at these epochs. Another possibility is that their spectra are being affected by unusual dust geometries inside these compact systems, making the interpretation of their energy sources more complex than standard analysis assumes. Both explanations are being tested with additional spectroscopic data. What's already clear is that the little red dots aren't a minor footnote. They're a new population of objects in the early universe, with no clean counterpart in modern observations and no straightforward home in existing theoretical frameworks. And the black holes at their centers are a problem in their own right, because those black holes have a mass problem that goes even deeper than the galaxies surrounding them. For a black hole to become supermassive, it needs to eat. Gas falls in, releases energy as radiation, and the black hole gains mass. This process, called accretion, is well understood from observations across cosmic history. The maximum rate at which a black hole can accrete is set by a physical limit, called the Eddington rate, the point at which the radiation pressure from infalling gas exactly counteracts gravity, preventing further accretion. Push a black hole above the Eddington rate, and the outward radiation pressure blows away the infalling gas. This limit sets a ceiling on how fast a black hole can grow. Starting from a seed black hole formed by the collapse of one of the first massive stars, a few tens of solar masses at most, growing to 1 billion solar masses or more at the Eddington rate would require hundreds of millions to over 1 billion years of continuous, uninterrupted accretion. The universe's first stars likely began forming around 100 to 200 million years after the Big Bang. That means the first stellar mass black hole seeds appeared around that time at the earliest. For a seed black hole to grow to 1 billion solar masses by the time the universe was 700 million years old, it would need to sustain near Eddington accretion for almost its entire existence, with essentially no interruption. That's already difficult to arrange physically. Accretion is often episodic, interrupted by the very radiation it produces, which periodically clears surrounding gas and pauses the feeding. Sustained near Eddington growth over hundreds of millions of years is theoretically possible, but requires specific gas supply conditions that models don't generically produce. Webb has now directly confirmed multiple supermassive black holes at extreme redshifts, with masses that strain this timeline severely. One object, a quasar confirmed by Webb at a redshift above 7, hosts a black hole with an estimated mass of several hundred million to over 1 billion solar masses, existing when the universe was under 700 million years old. Quasars had already been detected at such redshifts before Webb, using ground-based telescopes. Those detections had already created tension. What Webb adds is the ability to find not just the brightest, most luminous quasars, which are detectable because their extreme luminosity makes them visible across vast distances, but also lower luminosity active nuclei, sitting inside ordinary early galaxies. Webb is finding black holes that appear too massive for their host galaxies. In the modern universe, black hole mass and host galaxy mass follow a tight relationship. Bigger galaxy, bigger central black hole, inconsistent proportions. Several of Webb's early active galactic nuclei appear to have black hole masses that are large relative to their host galaxy's stellar mass, sometimes dramatically so. This suggests the black hole grew faster than, or ahead of, its surrounding galaxy, which inverts the sequence many models assume. Some researchers have proposed that the first black holes formed through a mechanism other than stellar collapse. Direct collapse black holes, forming from the direct gravitational implosion of an entire massive gas cloud, rather than a single dying star, would start with much larger seed masses, giving them a significant head start on growth. This remains a hypothesis. Direct collapse black hole formation requires specific conditions that may have been rare even in the early universe. But Webb's findings are making the alternative. Starting from stellar mass seeds and growing fast enough through standard accretion, increasingly difficult to sustain. The relationship between black holes and their host galaxies has always been one of cosmology's more intriguing puzzles. In the modern universe, the mass of a galaxy's central black hole tracks its host galaxy's mass with remarkable consistency. Measure the total mass of a galaxy's central bulge of stars, and you can predict its black hole mass to within a factor of a few. This tight relationship holds across an enormous range of galaxy sizes, from small ellipticals to giant seedy galaxies at the centers of clusters. The regularity implies a deep connection, a shared growth history, a feedback loop that links black hole feeding to galaxy building over cosmic time. The mechanism proposed to explain it is called AGN feedback. As a black hole accretes gas, it releases enormous energy in the form of radiation, and sometimes powerful jets of plasma. That energy heats the surrounding gas in the galaxy, and beyond it, into the wider galaxy halo, suppressing further star formation. This creates a self-regulating cycle. Black hole eats, releases energy, heats gas, slows star formation, and eventually slows its own fuel supply. The black hole and galaxy grow together, then together slow down. This feedback mechanism is a central pillar of modern galaxy formation models. Without it, simulations produce galaxies that are far too massive compared to what we observe. AGN feedback is what puts the brakes on galaxy growth and produces the realistic population of galaxies we see in the nearby universe. Webb's observations in the early universe are revealing that this relationship existed even at extreme redshifts, but with important differences. Multiple early galaxies with active central black holes show simultaneous rapid star formation and rapid black hole growth, consistent with both components building mass quickly at the same time. The coevolution is real and early. What's less clear is the ordering. In the modern universe, the tight black hole to galaxy mass ratio suggests they converged on their current proportions through a coupled history. In the early universe, Webb is finding systems where the black hole mass appears disproportionately large relative to the galaxy mass. If the black hole grew faster than the galaxy in the early universe, AGN feedback may have been shaping galaxy formation from very early on, possibly regulating even the first cycles of star formation in a way the models don't fully track. This early AGN feedback possibility has significant implications. If early black holes were already suppressing gas cooling and star formation in their host halos at redshifts above 6, that process would have been acting on the same gas supply that the model relies on to build early galaxies. Early suppression could mean that some halos failed to build large galaxies even though they had the mass to do so, while others managed bursts of intense star formation before feedback kicked in. The interaction between early black hole growth and early galaxy assembly may be key to explaining why the early universe looks the way it does in Webb's images. But tracing that interaction requires understanding what set the initial growth rates, and that path leads back again to the conditions set in the universe's very first moments. What's becoming clear is that the early universe was far more energetically active than any prior model assumed. Black holes, star formation, massive structures, all of them running faster and harder than the equations predicted. And the explanation may require revising something that sits at the very foundation of the cosmological model itself. In the very first fraction of a second after the Big Bang, before any atom, any star, any galaxy existed, the universe was imprinting a pattern. That pattern was invisible, microscopic, a set of tiny density ripples spread across a cosmos smaller than a grain of sand. Some regions had slightly more energy packed into them than others. The differences were extraordinarily small, roughly 1 part in 100,000, but they mattered enormously because they were the seeds of everything that came after. Every galaxy, every cluster, every filament, every void in the universe today traces its origin to those early density variations. The process that generated those seeds is called inflation. In the first unimaginably brief instant after the Big Bang, the universe underwent an episode of exponential expansion, stretching from subatomic scales to macroscopic scales in a fraction of a second. Quantum fluctuations, the random uncertainty built into physics at the smallest scales, were stretched by that expansion from quantum size to cosmic size. Those stretched fluctuations became the density ripples that gravity later amplified into structure. Inflation is one of the most well-supported ideas in modern cosmology, despite the fact that we have no direct observation of it. Its indirect fingerprints are all over the cosmic microwave background, the near-perfect uniformity of the background temperature across the entire sky, regions that should never have been able to communicate with each other under slower expansion, is explained by inflation stretching a tiny uniform patch to fill the entire visible universe. The specific pattern of temperature fluctuations in the background matches what simple inflation models predict. But inflation is a framework, not a single specific model. Dozens of different inflation models exist, each predicting slightly different properties of those primordial density seeds. One key property is called the tilt of the primordial power spectrum, describing how the strength of density fluctuations varies with scale. Another is whether fluctuations are Gaussian, meaning distributed randomly and symmetrically, or non-Gaussian, meaning slightly skewed toward having more extreme overdensities than a random distribution would produce. Standard lambda CDM assumes Gaussian fluctuations. The cosmic microwave background data is consistent with Gaussianity, though the precision of current measurements doesn't completely rule out small deviations. Here's why Webb's findings make this matter. If the primordial fluctuations had even a small degree of non-Gaussianity, meaning slightly more extreme overdensities than a purely Gaussian distribution, produces, those extreme overdense seeds would have collapsed earlier and more vigorously under gravity. Dark matter halos would have formed earlier and larger. Galaxies would have assembled faster. The early universe would look more structured, more massive, more organized than a Gaussian model predicts, exactly like what Webb is showing. The connection is speculative at this stage. Non-Gaussianity of the required magnitude to explain Webb's findings would need to be at a level that future cosmic microwave background experiments could potentially detect. Current data doesn't confirm it, but it also doesn't rule it out at the precision level needed. Researchers are actively working to quantify exactly how much non-Gaussianity would be needed to bridge the gap between predictions and Webb's observations, and whether that amount is consistent with existing measurements. The answer to that question would reach all the way back to the physics of inflation itself. Inflation solved several of cosmology's deepest problems all at once. The uniformity problem. Why does the cosmic microwave background look almost identical in every direction, even between regions of the sky that were too far apart to ever have exchanged energy before the background formed? Inflation answers this by stretching a tiny thermally connected patch to fill the entire observable universe before the background formed. The flatness problem. Why does the geometry of the universe appear almost perfectly flat, requiring the total energy density of the universe to be tuned to an extraordinary precision? Inflation stretches space so dramatically that any initial curvature becomes negligible, like the surface of a balloon blown to cosmic size appearing flat on any local patch. The monopole problem. Certain exotic particles predicted to form in the hot early universe, called magnetic monopoles, should be abundant if the universe cooled slowly, yet none have ever been detected. Inflation dilutes their density to undetectable levels by expanding the volume of the universe so rapidly after they form. These are real successes. They explain why the universe has the large-scale properties it does, and for decades, inflation sat as the near-universal consensus mechanism for the very early universe, even though its specific details remained debated. The debate centers on what drove inflation. The leading candidates are scalar fields, hypothetical energy fields, that could have briefly dominated the universe's energy budget, driving the exponential expansion. Different inflation models use different scalar field configurations and make slightly different predictions about the properties of the primordial fluctuations they generate. Most simple inflation models predict a nearly scale-invariant, nearly Gaussian spectrum of primordial fluctuations. That's consistent with cosmic microwave background observations, but nearly leaves room for small deviations, and those small deviations are exactly what Webb's findings might be probing. Some specific inflation models predict a mild enhancement of primordial fluctuations on certain scales. If those enhanced scales correspond to the scales relevant for forming the massive early halos Webb's galaxy clusters and filaments require, then those particular inflation models would predict more early structure than generic lambda CDM, and could partially explain Webb's observations. This is a live area of research. Several theoretical papers published since Webb's first deep field results began arriving in 2002 have explored specific inflation models that produce enhanced small-scale power and tested whether they're consistent with both cosmic microwave background constraints and Webb's structural observations. The answer so far is that some inflation models can produce more early structure without violating cosmic microwave background bounds, but the models required are more specific and more constrained than the generic picture usually assumed. An important caveat applies to this entire line of reasoning. Inflation is not yet a confirmed theory. Its indirect evidence is strong and broad, but a direct detection of the gravitational wave signature, predicted by inflation, called primordial B-mode polarization in the cosmic microwave background, has not yet been achieved. Several experiments are currently attempting this measurement, including the Simons Observatory and the planned CMB S4 experiment. If primordial gravitational waves are detected, the amplitude of that signal will constrain which inflation models are viable and whether they're the kind that could explain Webb's early structures. The outcome of those experiments, combined with continuing Webb observations, will either converge on a consistent picture or create a deeper fracture in the standard model than currently exists. Either way, the answer will require confronting the very first instant of the universe's existence. Reionization is one of the most important transitions the universe ever made, and Webb is revealing that it happened differently than we thought. In the universe's first few 100,000 years, matter was so hot and dense that protons and electrons existed separately, in a state called plasma. Light couldn't travel freely through this plasma. It scattered off the free electrons constantly. Then, around 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. The fog cleared. Light traveled freely for the first time. That light became the cosmic microwave background. But the hydrogen that filled the universe after this was neutral, and neutral hydrogen is extremely effective at absorbing ultraviolet light. When the first stars began forming and emitting ultraviolet radiation, that radiation was absorbed by the surrounding neutral hydrogen almost immediately. The universe, despite now containing light-producing stars, was still largely opaque to certain wavelengths. Reionization is the process by which the ultraviolet radiation from early stars and galaxies slowly ate away at the surrounding neutral hydrogen, stripping electrons from atoms and turning the cosmic gas back into plasma. Once the hydrogen was reionized, ultraviolet light could travel freely again. The universe became transparent. We know reionization was substantially complete by around 1 billion years after the Big Bang, because quasars observed at redshifts around 6 show relatively clean light transmission through the intergalactic medium. Before that, quasar spectra show strong absorption by neutral hydrogen. What remained uncertain before Webb was the detailed structure and timing of reionization. Was it a gradual, fairly uniform process driven by many small galaxies? Or was it patchy, driven by bright concentrated sources in already overdense regions, creating bubbles of ionized gas that expanded and eventually merged? Webb's observations strongly favor the patchy model. In its deep field images, it detects variations in the surrounding neutral hydrogen density around early galaxies, consistent with those galaxies having carved out ionized bubbles in their immediate environment. Early galaxy overdensities appear to correspond to regions where reionization proceeded faster, because there were more ultraviolet sources concentrated together. This has a direct implication for the connection between early structure and reionization history. If galaxy overdensities drove patchy reionization, and Webb is finding those overdensities to be more massive and more numerous than models predicted, then reionization may have proceeded faster and more unevenly than the standard timeline assumed. Some regions may have been fully reionized while others were still predominantly neutral. A spectroscopic study using Webb data, published in 2004, found evidence for a significant neutral hydrogen fraction persisting even at redshifts approaching 6 in some patches of the sky later than the smoothly completing reionization the standard model describes. Other regions appeared ionized earlier. The picture emerging is of a cosmic dawn that was more complex, more localized, and more tied to the distribution of early structure than any prior model captured. The massive early galaxies and protoclusters Webb is finding weren't just passive occupants of the early universe. They were the engines driving its largest phase transition. And when we look at the broader architecture they were part of, the cosmic web's earliest threads, the picture becomes stranger still. Distance tells you where a galaxy is in time. Spectroscopy tells you what was happening inside it. Webb's near-infrared spectrograph is capable of simultaneously capturing the spectra of hundreds of objects in a single observation, using a grid of tiny programmable shutters called a microshutter array. Each shutter opens over a specific target, allowing its light to enter the spectrograph while blocking everything else. The result is a simultaneous spectral analysis of hundreds of galaxies across a wide field in a single pointing. This capability transforms what was previously a slow, target-by-target process into a systematic survey tool, and the spectra it returns from early galaxies contain far more information than just redshift. The ratios of different emission lines in a galaxy's spectrum encode its chemical composition, oxygen, carbon, nitrogen, and other heavy elements each leave characteristic fingerprints at known wavelengths. Because heavy elements are produced inside stars and dispersed by supernova explosions, the abundance of heavy elements in a galaxy's gas is a direct record of how many generations of stars have already lived and died inside it. Webb is finding early galaxies with detectable heavy element abundances at redshifts that place them in the universe's first billion years. Some show oxygen abundances, suggesting multiple generations of star formation had already cycled through before we observed them. Stars were born, burned through their fuel, exploded and seeded the next generation, all within the universe's first few 100 million years. This chemical evidence is a separate and independent line of argument for early intense star formation. You don't get heavy element enrichment without stellar generations. Multiple stellar generations require extended, sustained star formation activity, beginning well before the observed galaxy's current epoch. Webb has also resolved individual star-forming regions inside some nearby early galaxies at moderate redshifts, something no prior telescope could do at those distances. The structure of those regions, compact, dense, intensely active, matches a mode of star formation that is more efficient than typical nearby galaxy conditions. For the most extreme early targets at redshifts above 10, individual star-forming regions aren't yet resolved, but the integrated light carries the chemical record, and several confirmed galaxies at these extreme distances show spectral signatures consistent with stellar populations that are already hundreds of millions of years old, meaning their stars began forming extremely close to the Big Bang itself. One particularly striking Webb observation involved a galaxy whose stellar population ages, inferred from its spectral energy distribution, implied that star formation began as early as 1 to 200 million years after the Big Bang. The galaxy itself was observed at around 300 to 400 million years. The math only works if the earliest stars in that galaxy lit up very soon after the universe began. This is a confirmed observational result, drawn from real spectroscopic data, not a simulation output, and it sits at the edge of what current models can accommodate. It also raises a question about those first stellar generations specifically, the very first stars in the universe, forming from primordial hydrogen and helium with no heavy elements whatsoever, should have been radically different from any star alive today, larger, hotter, shorter-lived, and nobody has directly detected them yet. Webb may be on the verge of changing that. Science progresses through disagreement, and right now, the disagreement about what Webb's early universe findings mean is genuine, substantive, and unresolved. On one side are researchers who argue the standard lambda CDM framework, with targeted modifications, can absorb Webb's observations without requiring a fundamental revision. Their case rests on several points. First, mass estimates for early galaxies carry real uncertainties. Photometric estimates can be inflated by active galactic nucleus contributions, unusual dust geometries, or specific assumptions about stellar populations. While spectroscopic confirmations have validated many findings, the most extreme mass claims still carry significant error bars. A galaxy initially estimated at 100 billion solar masses may confirm spectroscopically at 40 or 50 billion solar masses, which is still high but sits closer to the edge of what stretched model parameters might accommodate. Second, simulations are already evolving. Several groups have updated their galaxy formation models since Webb's first results to include higher early star formation efficiencies, modified feedback prescriptions at high redshift, and revised assumptions about early black hole seeding. Some of these updated models produce better agreement with Webb's high redshift galaxy counts, though the agreement is still imperfect. Third, cosmic variance matters. The early universe was not uniform. Some regions were genuinely overdense, forming galaxies and structures earlier than the cosmic average. Webb's deepest fields cover only small patches of sky. If those patches happened to intersect regions of the universe that were above average density, the observed galaxy counts could be elevated relative to the mean, without requiring a model revision that applies to the whole universe. On the other side are researchers who argue the accumulation of evidence now points to something more fundamental. Their case is equally grounded. The consistency of the excess across multiple independent survey fields weakens the cosmic variance argument. Webb's various deep programs point at different parts of the sky. They consistently return elevated galaxy counts at high redshift. The probability of repeatedly hitting above average density patches by chance decreases as the number of independent fields increases. The chemical evidence from spectroscopy is harder to explain away than photometric mass estimates. Multiple stellar generations at redshifts above 10 require a real and early star formation history, not a measurement artifact. The structure of early protoclusters implies real gravitational organization, not inflated brightness. And the little red dots, the early massive black holes, the cosmic vine and the protoclusters at extreme redshifts are not the same observation from different angles. They are different types of measurements pointing in the same direction. When independent observational techniques converge on the same anomaly, the probability of a systematic measurement error causing all of them simultaneously becomes difficult to maintain. The honest assessment from the field, as of the most recent conference proceedings and review papers, is that Webb has revealed a genuine tension that the standard model must confront. How deep that tension runs depends on spectroscopic follow-up, larger survey areas, and improvements in theoretical modeling that are all actively underway. The community is engaged, not alarmed. Productive tension is how cosmology moves forward, but it is real tension. And what drives the structure at the deepest level involves a cosmic architecture that runs through everything Webb has found. The cosmic web is the universe's largest feature, spanning billions of light years. It's the three-dimensional skeleton that organizes all of the matter in the observable universe. Superclusters of galaxies trace its densest filaments, enormous empty voids, regions tens or hundreds of millions of light years across, with almost no galaxies inside them, fill the space between. The web isn't a concept. It's a directly mapped structure, confirmed by galaxy surveys covering hundreds of millions of individual galaxies across the nearby universe. Lambda CDM successfully predicts the large-scale properties of the cosmic web at late times. The statistical distribution of filament sizes, void shapes, cluster masses, and large-scale matter correlations all broadly match the model's expectations in the universe as it exists today or in the relatively recent past. Webb is revealing the web's infancy, and that infancy looks more developed than the model expected. The most concrete signal is the distribution of galaxy overdensities at high redshift. Multiple Webb programs have identified regions of elevated galaxy density at redshifts between 4 and 8, corresponding to the universe between 700 million and 1.5 billion years of age. These overdensities are scattered across different survey fields, not concentrated in one direction that could suggest a local bias. Their statistical frequency, how often you find a region with significantly more galaxies than the cosmic average per unit volume, exceeds the predictions of Lambda CDM simulations at these epochs. Filamentary alignment is subtler but also present in the data. Several galaxy groups and protoclusters, identified in Webb fields, show elongated spatial distributions consistent with alignment along underlying dark matter filaments. This kind of alignment is expected in the cosmic web, but seeing it clearly defined at redshifts above 4 indicates the filamentary structure of the web was geometrically coherent at a point when models suggest it should have been far less organized. A separate but related finding comes from the spatial correlation of early galaxies. When astronomers measure how strongly early galaxies cluster together compared to random distributions, the clustering signal at high redshift is stronger than simulations predict. Stronger clustering means matter was more organized on certain scales in the early universe than the initial conditions fed into the simulations would produce. This clustering signal connects directly to the initial density fluctuations. If the primordial power spectrum, the mathematical description of how density varied with scale, just after the Big Bang, had slightly more power on small scales than the standard model assumes, galaxy clustering in the early universe would be enhanced. The early Webb would look more developed. The observations would match. The amount of extra small-scale power required to explain the enhanced clustering is being actively calculated. Whether it's consistent with cosmic microwave background constraints, which provide the most precise measurement of the primordial power spectrum, is one of the key diagnostic questions now driving theoretical work in cosmology. The answer matters because if the primordial power spectrum differs from what lambda CDM assumes, the adjustment doesn't stay in the early universe. It propagates through all of cosmic history, affecting structure at every subsequent epoch. Every structure Webb observes is connected to every structure observed in the nearby universe by the same unbroken chain of gravitational evolution. Pull on the thread in the early universe, and you feel it all the way to today. One unexpected galaxy can be a fluke. A dozen scattered across independent fields, observed by different instruments, confirmed through different techniques, all showing the same anomalous properties, crosses into a different kind of argument. Statistics doesn't care about the elegance of a model. It responds only to what the data actually shows. The statistical case against the early universe, looking exactly as lambda CDM predicted, has been building since Webb's first data releases, and it has grown more coherent with every subsequent observation cycle. Here's how that case is structured in practice. Researchers take the predictions of lambda CDM, specifically the expected number of galaxies above a certain stellar mass at a given redshift, and compare them to what Webb actually counts in a survey field of known area and depth. The ratio of observed to predicted gives a measure of the tension. In the first Webb results, some comparisons returned ratios of 10 to 1. Observed galaxy counts at extreme redshift exceeded model predictions by an order of magnitude. As spectroscopic follow-up, refined distances and masses, some of those ratios came down. Photometric overestimates were corrected. Some candidates were reclassified. The honest picture became more nuanced. What remained after that refinement was still a statistically significant excess. A systematic comparison, published using data from multiple Webb survey programs, found that the number of galaxies with high stellar masses at redshifts above 7 consistently exceeded lambda CDM predictions by factors of several, even after conservative assumptions about mass estimation. That excess didn't vanish with better data. It became better measured. The significance of this consistency across fields is important to quantify. Webb has conducted deep observations through several independent programs. The JADES program targeting the well-studied GOODS fields, the CERAS program in the extended Groth strip, the PRIMA program covering wider areas at moderate depth, and others. These programs differ in strategy, depth, and sky location. Their high redshift galaxy counts, when compared to model predictions, return consistent elevated results. The probability of an elevated count in one field being a cosmic variance fluke is manageable. The probability of independent fields all returning elevated counts in the same direction simultaneously decreases rapidly as the number of independent fields grows. Across 5 to 6 independent Webb survey fields, all showing consistent excess, cosmic variance alone is a difficult explanation to sustain. There is a second, complementary statistical argument involving not just galaxy counts, but the extreme upper end of the galaxy mass distribution. In statistics, the tail of a distribution, the region containing the rarest, most extreme cases, is particularly sensitive to the underlying process generating the distribution. Small changes to that process produce large changes in how many extreme mass galaxies exist. Lambda CDM predicts the mass distribution of early galaxies and specifies how rare galaxies above a given mass threshold should be. Webb keeps finding galaxies above those thresholds in numbers that push the tail of the distribution far above the prediction. The tail is too fat. Too many extreme objects exist, and a fat tail in a mass distribution is a direct signature of an underlying physical process that is either more efficient, more variable, or started from larger initial seeds than the model assumes. Statistical arguments alone don't tell you which physical revision is required, but they tell you clearly that one is. The early universe had a finite amount of matter to work with. That matter, ordinary baryonic material like hydrogen and helium gas, dark matter, and the energy content driving expansion, was set at the Big Bang and has been conserved since. The universe didn't gain mass. It reorganized it. Structure formed by matter moving from smooth, diffuse distributions into concentrated halos, filaments, and clusters under gravity. If more matter was locked into massive structures in the early universe than the standard model predicts, that has a direct consequence. Less matter was available for the structures that formed later. This matters for the intermediate universe epoch, the period between about 2 and 8 billion years after the Big Bang, when the bulk of today's galaxy population assembled. Lambda CDM makes predictions about galaxy mass functions during this period. How many galaxies of each mass should exist at each epoch? These predictions have been cross-checked against large surveys for decades and work reasonably well, but they were calibrated against a model where the early universe had a specific amount of mass already locked into early structures. If that amount was significantly larger than assumed, the available gas supply and dark matter halo distribution at later epochs would differ from what the model uses as its starting point for intermediate-era galaxy formation. The consequence is subtle but real. Certain galaxy populations in the intermediate universe might be slightly less abundant than observed, or their assembly histories might appear shifted in time compared to predictions. Researchers are beginning to examine whether the anomalies in the early universe, taken at face value, predict any downstream inconsistencies in the intermediate-era galaxy population that could be tested with existing survey data. This is the forward-propagating constraint. Webb's early universe findings aren't confined to the high redshift window. If the initial conditions were different, the entire evolutionary chain that follows is affected. Tracing those effects through cosmic history becomes a way to test whether the early universe modifications implied by Webb are physically consistent end to end. There's a parallel implication for the distribution of voids, large underdense regions. The cosmic voids that make up the bulk of the universe's volume are the counterpart to overdense structures. If matter concentrated more aggressively into early structures than predicted, the surrounding regions were depleted more rapidly, potentially creating larger or deeper voids than the standard model expects at corresponding epochs. Void statistics in the modern universe provide an independent test. Several analyses of large-scale structure surveys have reported that the largest voids in the observed universe appear slightly larger than lambda CDM simulations predict. This has been discussed as a potential signature of enhanced early structure formation, though the statistical significance of the void size discrepancy is debated. The interconnectedness of these signals, early massive galaxies, overdense protoclusters, early cosmic web structure, downstream void statistics, and intermediate-era galaxy populations, is what makes Webb's findings more than a single isolated telescope result. They're a pressure point that propagates through the entire cosmological model, and the model wasn't built to absorb pressure from so many directions simultaneously. Everything Webb is finding about the early universe has implications for a question closer to home. How did our galaxy come to exist? The Milky Way is a large spiral galaxy, sitting within a small group of galaxies, bound together gravitationally with a few dozen neighbors, in what astronomers call the local group. The local group itself is on the outskirts of a larger structure called the Virgo supercluster, which is in turn part of an even larger assembly called the Laniakea supercluster, a vast sheet of galaxies spanning roughly 500 million light-years. All of this structure traces back to the same primordial density seeds that Webb is now probing at extreme redshift. The overdense region of the early universe that eventually became Laniakea was set in place by the initial conditions of the Big Bang. The Milky Way formed inside a dark matter halo that began collapsing in the early universe, in an environment shaped by its neighbors. If the early universe was more structured, more aggressively organized than lambda CDM predicts, then the environment in which our galaxy formed was more crowded, more dynamically active, more intensely star-forming than our standard model describes. Protoclusters and massive early galaxies would have been more common in the volume that eventually became our cosmic neighborhood. The radiation, the energetic feedback, the gas dynamics of that denser early environment would have shaped the conditions available for our galaxy's formation. This doesn't change the Milky Way's present-day properties. Our galaxy exists as we observe it, with its specific mass, structure, star formation history, and chemical abundances. What it changes is the story of how it got here, the Milky Way's formation history. The sequence of mergers, gas accretion episodes, and star formation bursts that built it was embedded in a specific large-scale environment. That environment was shaped by what surrounded it in the early universe. One concrete connection involves the Milky Way's ancient stellar population. Our galaxy contains stars that are extremely old, some approaching 13 billion years, born in the galaxy's earliest phases. The timing and conditions of that initial star formation episode were set by when and how the dark matter halo that seeded the Milky Way assembled. If halos assembled earlier and more aggressively than the Standard Model predicts, the Milky Way's earliest stars may have formed under conditions more extreme than the standard history assumes. The chemical record of those ancient stars, encoded in the abundances of elements in their atmospheres, carries information about the environment they formed in. Current and upcoming surveys of ancient Milky Way stars, including data from the European Space Agency's Gaia mission and future spectroscopic surveys, are building a detailed chemical map of our galaxy's stellar populations. Comparing that map to the predictions of galaxy formation models under both standard and revised early universe conditions provides another independent test of what Webb is finding at extreme redshift. The early universe that Webb is revealing and the ancient history of our own galaxy are part of the same story. And reading that story clearly requires the most complete measurement of the universe's expansion we can construct. Before Webb launched, cosmology already had a problem it hadn't resolved: the Hubble tension. The Hubble constant is the number that describes how fast the universe is expanding today. Expressed simply, for every 3.3 million light-years of distance between 2 points in the universe, those points are moving apart at a rate described by the Hubble constant. Measuring this constant precisely is one of the central goals of observational cosmology. The problem is that two independent measurement methods give different answers. The first method uses the cosmic microwave background. By precisely mapping the temperature fluctuations across the entire sky, physicists can fit the entire cosmological model and extract the Hubble constant from those measurements. The Planck satellite measurement from this method gives a Hubble constant of around 67 kilometers per second per megaparsec. The second method uses the cosmic distance ladder, a chain of distance measurements starting with nearby objects whose distances can be measured geometrically, anchored to variable stars called Cepheids, and extending to supernovae in distant galaxies whose peak luminosity is known. The distance ladder measurement, refined over years by teams including the SH0ES collaboration, gives a Hubble constant of around 73 kilometers per second per megaparsec. These two numbers disagree by roughly 9%. That disagreement has been measured to a statistical significance, where a random chance explanation is considered essentially ruled out. Both measurement chains have been checked independently multiple times by different groups using different instruments. The tension is real. Webb has entered this debate directly. One of Webb's early programs used its infrared precision to re-examine Cepheid distance measurements in nearby galaxies that form the foundation of the distance ladder. The goal was to check whether systematic errors in Hubble's Cepheid measurements might have inflated the distance ladder Hubble constant. The Webb Cepheid measurements were published in 2203. They confirmed the SH0ES distance ladder results. The higher Hubble constant value did not go away when re-examined with Webb's superior infrared precision. The Hubble tension survived the check. This matters for the early structure problem because the Hubble constant encodes how fast the universe expanded. A higher expansion rate changes the age-distance relationship in cosmology. A universe expanding slightly faster than the Planck measurement suggests would be slightly younger at a given redshift, compressing the timeline for early structure formation even further. Now add Webb's structural findings as a third independent line of tension, alongside the Planck versus distance ladder disagreement. Three separate observational pressures, each well measured, each pointing in the same direction, toward an early universe that was more active, faster developing, and differently calibrated than lambda CDM's baseline predicts. Three independent tensions don't prove a single unified explanation exists, but their simultaneous presence in the same framework makes it increasingly difficult to attribute all three to independent, unconnected measurement errors. The possibility that they share a common root, something about the initial conditions or the energy content of the early universe, is being taken seriously by researchers across the field. Whether that shared route requires a small patch to existing physics or something more substantial is the open question that will define the next decade of cosmology. Cold dark matter is the default, but cold is an assumption, not a certainty. When physicists say dark matter is cold, they mean its particles were moving slowly relative to the speed of light in the early universe. Slow-moving particles can clump on small scales easily because they don't have enough kinetic energy to escape small gravitational whirls. Cold dark matter therefore produces small halos first, which merge into larger ones over time. The hierarchy runs from small to large, bottom to top. Warm dark matter is a different possibility. Warm dark matter particles would have been moving faster in the early universe, too fast to be captured by small gravitational wells. This suppresses the formation of small halos. Warm dark matter wipes out structure below a certain mass scale, determined by how fast the particles were moving. Above that scale, structure forms normally. For decades, warm dark matter has been constrained by observations of small-scale structure, the distribution of satellite galaxies around the Milky Way, the properties of small dwarf galaxies, and the pattern of matter clustering on small scales all provide upper limits on how warm dark matter can be. Pure warm dark matter models with high particle velocities are ruled out because they erase too much small-scale structure compared to what we observe. But there's a range between pure cold and pure warm, where the behavior is more subtle. Models with a small warm component mixed into a predominantly cold dark matter framework, or models where dark matter interacts slightly with other particles in the early universe, can produce modified halo mass functions that differ from pure cold dark matter predictions on specific scales. Some of these modified dark matter models predict enhanced structure formation on intermediate scales, precisely the scales relevant for the massive halos that Webb's early galaxies and protoclusters appear to inhabit. The idea is that if small halos are partially suppressed by a warm or interacting dark matter component, matter that would have gone into small halos instead flows into intermediate and large halos, potentially boosting their mass. This is an active area of theoretical investigation, not a confirmed explanation. The modified dark matter models that help with early massive structures often create other tensions with small-scale observations that need to be carefully managed. The parameter space is constrained from multiple directions simultaneously, leaving only narrow windows for models that improve the high redshift picture without breaking what already works. What makes this theoretically productive is that Webb is now defining the observational targets precisely enough for these models to make testable predictions. If a specific warm-dark matter mixture predicts a specific modification to the galaxy mass function at a given redshift, Webb can in principle test that prediction directly with sufficiently large spectroscopic samples. This is the scientific loop closing. Webb's anomalies aren't just puzzles sitting in isolation. They are becoming specifications for what a correct theory of dark matter needs to produce. And as the specifications sharpen, the space of allowed dark matter models narrows. The narrowing of that space is pointing toward experiments that extend well beyond telescopes. Underground detectors hunting for dark matter particle interactions, particle accelerators probing high-energy physics, and the next generation of cosmic microwave background experiments looking for signals in the oldest light in the universe, all of them connected by the same thread Webb is pulling. Webb is operating, the data is flowing, and the scientific community has built a roadmap for testing everything the first 3 years of observations have raised. The most immediate priority is spectroscopic follow-up at scale. Imaging detections generate candidates. Spectroscopy confirms or revises them and extracts the detailed properties that imaging cannot. Webb's remaining operational lifetime, estimated conservatively at over a decade based on its fuel reserves, allows for systematic spectroscopic programs targeting hundreds to thousands of early galaxy candidates across multiple survey fields. Several large programs are already underway. The JADE's Origins field, a Webb deep field targeting the most extreme redshifts with an unprecedented combination of depths and spectroscopic coverage, is designed to systematically confirm galaxy populations and map their properties from redshift 4 all the way to the edge of detection above redshift 13. As that program delivers results, The statistical samples will grow large enough to distinguish between model adjustment scenarios and more fundamental revisions. Parallel ground-based follow-up is accelerating. The Atacama Large Millimeter Array, a radio telescope array in Chile, detects cold gas and dust emission from early galaxies at wavelengths complementary to Webb's infrared window. Combining Webb's stellar population data with radio observations of gas content gives a more complete picture of how early galaxies were actually assembling their mass. Several dedicated programs combining Webb and Atacama Large Millimeter Array data are running simultaneously. The Vera C. Rubin Observatory, a wide-field ground-based survey telescope scheduled to begin its legacy survey of space and time in the mid-2020s, will map tens of billions of galaxies across a massive area of sky. While it can't reach Webb's depth or resolution, it provides the statistical context that Webb's deep but narrow fields need. Large area surveys reveal the cosmic average. Deep narrow surveys reveal the extremes. Together they constrain the full distribution. On the theoretical side, next-generation cosmological simulations are incorporating Webb's observational constraints directly into their calibration. Groups running updated versions of Illustris-TNG and new simulation frameworks are testing whether modified early star formation efficiencies, different dark matter prescriptions, or adjusted primordial power spectra can reproduce Webb's findings while remaining consistent with the full observational record across cosmic time. Crucially, the cosmic microwave background experiments now in development and deployment will independently probe the primordial fluctuations that may be driving everything Webb sees. The Simons Observatory has begun operations. CMB S4 is in development. These instruments will measure the primordial power spectrum at higher precision than currently available, testing whether non-Gaussianity or enhanced small-scale power exists at the level required to explain early structure formation. Every one of these programs is producing new data within the next 5 years. The convergence of Webb, next-generation ground observations, and cosmic microwave background precision measurements is expected to either tighten the tension into an undeniable crisis for lambda CDM or identify the specific physical modification that resolves it. Either outcome moves cosmology forward. Both outcomes are scientifically valuable, and both require the data that's now actively arriving. The answer is close. The timeline is measurable, and when it arrives, it will reach back to the very first moment of the universe's existence. Webb has done something that telescopes rarely manage to do. It hasn't just answered questions. It has revealed that the questions we were asking were incomplete. The universe that lambda CDM described was a universe of gradual accumulation, slow growth, patient hierarchy, matter assembling itself across vast stretches of time, building from the smallest seeds into the grand structures visible today. That picture was built carefully, tested rigorously, and validated against every observation available before Webb launched. And it was missing something. What Webb has revealed, across dozens of independent observations using multiple instruments and techniques, is that the universe had an early chapter of organization that the model didn't fully account for. Massive galaxies forming in the universe's first few 100 million years, black holes growing to enormous mass before any known mechanism can comfortably explain, filamentary structures coherent and massive at epochs when they should barely have begun taking shape, protoclusters in the universe's first 700 million years, a cosmic web with threads visible far earlier than any simulation predicted. Each of these observations is real. Each is supported by direct measurement. Each has survived, in some form, the process of spectroscopic confirmation and critical scrutiny that science requires. Together they outline a universe that organized itself earlier, faster, and more aggressively than we knew. The implications spread in every direction. If the primordial seeds were larger than assumed, inflation worked differently than the simplest models describe. If dark matter clustered faster than cold dark matter predicts, its particle properties may differ from the standard assumption. If early star formation ran at efficiencies well beyond any modern analog, the physics governing gas collapse in the early universe was operating in a regime we haven't directly observed. If early black holes grew too massive too quickly, their seeding mechanism and accretion history require a revision. These aren't separate problems with separate solutions. They share an origin. The early universe's hidden chapter of accelerated organization connects all of them through the same physical conditions, the same initial density field, the same dark matter behavior, the same feedback dynamics, operating in the universe's first few 100 million years. The honest status of the field, as of the most recent data, is that no single theoretical proposal fully resolves the tension. The model is under genuine pressure. Some researchers expect the pressure to ease as data quality improves and mass estimates tighten. Others expect it to intensify. The data itself will determine which expectation proves correct. What is certain is that the universe Webb is showing us is more active, more organized, and more complex in its early history than the map we drew before we could see it. Every week, new Webb spectra arrive. New confirmations or revisions get published. The picture sharpens. We sent a telescope to look at the beginning of everything, and what it found was a universe that had already been busy for a long time before we thought it started. The standard model of cosmology isn't broken, but it has a door that was assumed closed, and Webb has opened it. Behind that door is the universe's earliest chapter. We are only a few pages in,